Hello everyone, I am Spandan De. Today I am going to present my paper that has been accepted in ICDIPC 2019 titled as Design of a Real-Time Automatic Source Monitoring Framework based on Sound Source Localization. The authors are Spandan De, Srinivas Boppu and M. Sabarimala Manikandan. Real-Time Embedded Signal Processing Lab, School of Electrical Sciences, Indian Institute of Technology, Bhubaneswar, India. These are my presentation outlines: introduction, motivation and problem statement, literature review, design process and methods, implementation results, conclusion and references. Sound source localization is a technique to estimate the location of a sound source with the help of only the sound coming from it. The basic block diagram of sound source localization system is shown. It uses microphone array. From microphone array, features are extracted. With the assumption of propagation model and a mapping function, these features are mapped into locations. The important features are time difference of arrival, inter-microphone intensity difference. Propagation model assumptions are near field, far field, where flat sound waveform is assumed, and Wordsworth-Kolsberg model used in robotics. The mapping functions that are used in literature are correlation-based method, beamforming method, and learning-based method. The major applications of sound source localization is human interaction in robotics, such as robot acting as waiter in target tracking, detection of source of certain sounds sounds in space, audio surveillance, automatic camera movement in conference, and it is also used as pre-processor block in applications such as speech enhancement and speech recognition. The challenges in sound source localization are, of course, degradation of localization performance in the presence of noise and reverberation, real-time tracking and localizing of multiple moving sources, selection of proper microphone array, no response for unwanted sound sources, and localization only for desired sound source. The problem statement is defined as developing an automatic source monitoring framework based on sound source localization model with the following specifications. The models would be real-time, accurate, low cost, and smaller in size. Indication of localization output should be present to monitor the source. Localization task would only be done for specified classification of sound, such as pitch or other kind of classifications. The developed framework should not respond to unwanted classes of sounds. These are the summary of recent literature survey. As it can be seen, in the recent trend in sound source localization is to use deep learning and machine learning. In paper 1, the authors tried to localize a sound source with single microphone. They have used non-negative matrix factorization. Paper 2 uses RBF neural network based on global k-means clustering. Two sources were located with the help of 3 microphones. Paper 3 locates a single speech source with binaural recording set using deep learning. Paper 4 uses to localize a single source with 2 microphones, and they used bio-inspired computational model. Coming to implementation, we have designed 2 hardware setup. One is Arduino based framework and another is Raspberry Pi based framework. While designing, we have faced some design issues. These are number of microphones in the array, microphone range, array geometry, and inter-microphone distance. This is the experimental setup of our Arduino based framework. It uses Arduino Mega ADK, 4 or 8 microphone sensors and stepper motor. These are the detailed system specification of our first framework. It is implemented in 4 microphone as well as 8 microphone model. ADRAX CZN15E sound sensor is used. For automatic camera steering, stepper motor 28 BYJ48 with ULN 2003 driver is used. Distance of microphones from array center is 10 cm. Bluetooth speaker is used as source. TV beep sound, ping sound, clap and speech used as types of sources. LED attached to sensors with highest received average sound intensity will glow. This is the algorithm. First, separate out all channel recordings. Then calculate the mean of each of them. Calculate the power by squaring its amplitudes. Then normalize each channel with respect to the mean value of the recorded channel data. Then sum the channel recorded data. The channel with maximum final value indicates the direction. This is how we conducted experiment using our first framework. Angular view, that is the azimuthal 360 degree plane, is divided into 8 segments, 45 degree of each for the case of 8 microphone. For 4 microphone setup, azimuthal plane has been segmented into 4 regions. The 8 regions are north, northeast, east, southeast, south, southwest, west and northwest. The source is traversed through each of the region both in near field and far field. The microphone with highest mean normalized intensity value estimates the direction of arrival. If stepper motor rotates towards the current location of the source, it is considered as hit. Otherwise, it is considered as miss. The hit ratio is the performance metric for the evolution of this framework. This is our second framework. We used Raspberry Pi and rich speaker microphone array. The microphone array specifications are given. The number of microphones are 4. Array geometry is square. Range is 3 meter and 12 programmable LEDs are there to monitor the source. We use generalized cross-correlation phase transform algorithm. Localization task for the second framework was performed with various kinds of sounds: speech, clap, dog barking, music instruments and background noise. Recording with varying source to microphone distance has also been carried out. Once, recordings were done in near field where the source to microphone distance is 1 foot, and in far field scenario the source to microphone distance is 2 to 3 meters. Using our second framework, we have designed a keyword classified localization system. We used a trained DNN based model. It estimates the source location if and only if the source says the correct keyword. In case of any other sound, no localization task is done. The block diagram of our keyword classified localization is shown. First, the model is trained with several number of recordings of the same keyword. Then while testing phase, the model classified our keyword whether it is correct keyword or not. If it is correct keyword, then only the GCC-PHAT module is activated and the source is localized. Coming to results, this is the performance evaluation table of our first framework. The upper table denotes the results when 8 microphones has been used, and the lower table used the results for 4 microphones. We have given the results for near field and far field, and with background noise and without background noise. Here the background noise are AC, fan and people speaking that noise. As it is obvious, the best case is achieved when the source is in near field and no background noises are present. The worst case is when the source is in far field and background noise is present. The best result we have got in case of 4 microphone system when the source is in near field and no background noise is present, that is 100%. The worst case result has been achieved when the source is in far field and in the presence of background noise. The worst case accuracy is 70%. This is the performance evaluation of our second framework, that is the Raspberry Pi based framework. The green line denotes the ideal direction of arrival. The blue dots denotes the estimated direction of arrival by our own framework, whereas the red dots is the estimated direction of arrival done by the standard delay and sum algorithm. As you can see, the blue dots are more inclined with the ideal line as compared to the red dots, which indicates that our framework outperforms in localization the standard delay and sum beamformer. This figure denotes the average estimation error and is compare our average estimation error with the standard delay and sum beamformer. Two scenarios are there. The left bars denote when the source is in noise-free environment and the right bar denotes when the source is in noisy environment. As it is clearly seen, the blue bar, which denotes our own estimated estimation error, is much less as compared to the orange bar, which is due to the standard delay and sum beamformer. This is the performance evaluation table of our keyword detection and localization. This table denotes the detection accuracy for varying distance and noise level. We have used a Bluetooth speaker and we have mixed a relative noise level with the keyword and played it with the Bluetooth speaker. And we varied the Bluetooth speaker for the distance of 1 foot, 1 meter and 3 meters. As it can be seen that the detection accuracy decreases with the increase in distance as well as increase in noise level. One important thing to mention that detection performance is better for female voice as compared to male voice. The solution is to train the used model with a larger and more diverse data. This is the localization performance of our keyword detection and localization framework. The red bar denotes the actual direction of arrival. The yellow bar denotes the estimated direction of arrival of our framework and the blue bar is due to the delay and sum beamformer. As it can be seen in the figure, the yellow bar and the red bar are more closely related as compared to the blue bar, which denotes that in case of keyword detection and localization, our design framework outperforms the standard delay and sum beamformer. This is the comparative table of both the frameworks that we have designed. In case of Arduino based framework, we have designed the microphone array manually, whereas in case of Raspberry Pi, it is inbuilt. We have used 8 microphones in first framework as well in 4 for the second. The angular resolution is 45 degree for first framework, whereas for second framework, we have achieved an angular resolution 15 degree with average estimation error of minimum 3.6 degrees. For source monitoring, for the first framework, we have used stepper motor, whereas for the second Raspberry Pi based framework, we have used programmable LEDs. Coming to conclusions, both the frameworks designed are real-time, cost-effective and used simple hardware. Arduino based first framework is affected due to background noise as it is based on intensity difference method. It has angular resolution of 45 degrees. Raspberry Pi framework is robust to noise. It has angular resolution of 15 degree with minimum average estimation error of 3.6 degrees. The second framework can be used as bird call identifier and localization. Another future scope is to use more diverse model and make our sound source localization as personalized as it can be. We would like to express our acknowledgement to School of Electrical Sciences, IIT Bhubaneswar. This research work was carried out as a part of the cluster projects of the Special Manpower Development Program for Chips to System Design under Ministry of Electronics and Information Technology Grant, Government of India. These are the references. Thank you.